Hi again, and welcome to the third part of Lecture 5. In this one, we will establish some fundamentals of ISM kinematics, and in particular, take a closer look at the rotation curves of disk galaxies and what we can learn from them. Going back to the basics from Newton's law of gravity, we can define the gravitational potential phi as a function of the position vector x. And this is going to be solved as this rather unpleasantly looking integral equation that we see here. What that says is that the potential felt by a test particle at position x, resulting from the combined gas density integrated over all positions x prime, is given by this expression here. But that means that in principle, we would need to integrate over the entirety of space in order to solve this equation. We can turn this into a differential equation, the Poisson equation, which states that the divergence of the gradient of the gravitational potential is given as simply 4 pi times the gravitational constant times the density in the point x. Together with Newton's shell theorem for spherically symmetric systems, in these particular cases, we can simplify things a great deal. This theorem states that the gravitational force inside a spherical shell of uniform density is 0, and outside any spherical symmetric object, the gravitational force is the same as if all the mass were concentrated at the center. So if we think about that for a little while, that means that if we have a spherically symmetric mass distribution and we find ourselves as a test particle at some distance from the center, denoted r, then all gas or all mass on a distance larger than r from the center can be simply ignored, discarded, because all the contributions to the gravitational force from this gas simply cancel out, and therefore will end up being 0 net. And inside our distance r, we can simply assume that all the gas at a lower distance than us is concentrated in one single point in the center of this spherically symmetric distribution. And of course, this can greatly simplify things for us in these simplified conditions. And as it turns out, quite often many astrophysical systems are quite nicely approximated as more or less spherically symmetric systems. This theorem leads to this expression here, which states that the circular velocity at radius r is given as this function here, depending on the gravitational constant, the distance r, and the mass enclosed within this distance r. This circular velocity is defined as the velocity at which the gravitational potential at the radius r is exactly balanced by the circular velocity, such as that this velocity will be perfectly tangential, therefore circular, to the radius vector, and that this will lead to a perfect circular stable orbit around the center of mass of this system. For a given density profile rho of r, we can then derive the rotation curve, which is simply the circular velocity as a function of r. And we can then compare that to observed values of these curves in various galaxies to measure the mass distribution in these galaxies. So here are some examples of relatively simple theoretical density profiles. This here is the isothermal sphere. Here we have a simple power law, and in the center we have a so-called NFW profile. None of these are perfect descriptions of real-life systems, but they are, as we can see over here to the right, not super far off either. Here we have the Here we have the circular velocity profile of an actual real galaxy. And we can then overplot some of these density profiles, or rather the rotation curve, the theoretical rotation curve derived from these density profiles, and compare them to the real thing. As mentioned before, we like to use the 21 centimeter line of neutral hydrogen to map velocities of gas for two reasons. First, because the velocity measurements that we get at these wavelengths are very accurate. And second, because this gas, as also mentioned earlier, stretches out to much larger extents than the stellar population, so we can probe much larger radii compared to the stellar population. But what we then measure in these cases is, of course, an apparent velocity relative to us. But that apparent velocity can be misleading for two reasons. First off, the galaxy is seen at a certain inclination, right? We are not looking at it completely face on. We're not looking at it completely edge on either. We're looking at it in some angle. And so that angle is called the inclination angle I. But also, wherever we're looking at a point, we're only looking at the component of its velocity, which is along our line of sight. But at any point in a rotation in such a galaxy disk, there will also be a transverse component, and we need to be able to correctly translate the observed line of sight velocity component to a true circular velocity component. And we can do that by using the formula that we see here, where the projected velocity, that is the line of sight velocity component, is equal to, first off, the systemic velocity of the galaxy, which is important in practical observations, but not very theoretically interesting, because it is just the velocity of the galaxy as a whole, whether it is on its way away from us or towards us for various reasons. But then, of course, the circular velocity times the sine of the inclination times the cosine of this phase angle phi, which is an angle relative to the transverse direction. And we can map this projected or apparent velocity, and we get this thing here that we call spider diagrams, where these things are simply curves of equal apparent velocity or equal projected velocity, you can say. With that as a starting point, we can then look at various galaxies and derive, and from these contours of constant projected velocity, we can derive an actual like radial velocity profile, which then shows us the mass distribution within the galaxy. And what we can see here is three examples of various types of galaxy observed in this manner. In the left column, we have an SA galaxy, that is one with a very prominent bulge and tightly wound spiral arms. In the center column, we have an SC galaxy, so one that does not have a very prominent bulge and less tightly wound spiral arms. And finally, in the right column, we have a dwarf irregular galaxy, which doesn't really have any bulge at all in the center. And we can see, if we look at this row here, which maps the integrated velocity over a slice as a function of its distance from, not the integrated, but the velocity distribution as a function of its distance from the center. And you can see that the curve we get out of this has a lot of the mass, well, a lot of the emission, and therefore also a lot of the mass, sitting at relatively narrow velocity distributions here and here. So this is the distance axis and this is the velocity axis, right? With this here being the systemic velocity of the galaxy itself, the average velocity of the galaxy itself. And what we see here is that there's a very sharp jump in this galaxy from this velocity to this velocity. Then it actually falls a little bit before it settles on a constant value. If we look at the one over here, we can see that the jump is less sharp, but there's actually an even larger fraction of this galaxy that is concentrated, as you can see here, here, and here, at this one or these two mirrored constant velocities. And given that the 21 centimeter light that we're looking at these in is optically thin, that means that mass and number of photons follow directly from each other. That means that if we have a lot of mass concentrated at this velocity and this velocity, then we will also have a lot of light concentrated at this velocity and this velocity, which is exactly what we see in these profiles here, where we can see that these two spiral galaxies both have these famous double-horned velocity profiles. We can also see that in the dwarf irregular, we don't really see any horns because there isn't really any constant velocity that any gas is settled on in this galaxy. Its rotation curve profile, it grows or it sinks, but it doesn't actually settle at a constant value anywhere that we can notice. So that one is much closer to the typical Gaussian profile that we would see if the majority of the gas was distributed in a thermal way rather than in a rotating disk. The peak separation in the double horn profile is given or corresponds to the physical properties in the disk by this formula. And that means that we can also actually use the peak separation in this double horn profile to estimate the mass of the rotating disk. That was it for now. Now I would like you to think a little bit about this week's discussion or this session's discussion questions. These are question A. What does it mean that the ISM is cooled? Why is the process important to understand? The warm ISM in H2 regions is cooling quite efficiently, but the likewise warm ISM or even hot ISM of elliptical galaxies cannot cool down very efficiently or at all. What is the difference? Why could that be? And question B, why does the rotation curve have different shapes in different types of galaxy? Why are they not all the same? Why is there a different slope around the center? Why do some galaxies seem to settle down to more or less constant rotation velocity, while others don't seem to have such a constant rotation velocity worth noticing? So please mull these over until we meet, and then we will discuss these questions. And that was all for now. Thank you for staying with me this far, and I will see you around in the next one. Bye.